kiddos. Wave to the camera.
There's no camera.
All right. Okay.
I played along.
Sophie's still looking good.
You still wave.
Sophie's the
You're gonna look goofy. I can't wait to show this to your mom on her birthday. It'll be fun. So, all right. Okay. So kids, 4.2, like I said, it's gonna get kind of lengthy, and there's gonna be a lot of rules in here that we have to remember. And I don't want to tell you it's going to get difficult, but there are so many rules that you're going to have to sort through to try and keep things straight. So what I'm going to tell you is this: the better you can take notes today, and the more you refer to your notes as you go through some of the problems, I think that's going to help you be successful. So I would have these notes pretty close by when you're going through the assignments when we get those sent out. I think you'll handle this pretty well. I'm going to tell you it's going to start out pretty easy, but then it's going to move all of a sudden like kind of difficult. And I don't mean that to scare you, but there's just so many different properties here and so many different rules and so many different ways of doing things that it's going to get a little confusing. So you're going to have to be persistent doing this stuff. And I got to tell you, if you get stuck, talk to your peers. Talk to your peers, because some of their ideas might be something that you don't think about. So I'd strongly encourage you to discuss your work with each other, okay? All right, so guys, in 4.2, titled Properties of Rational Exponents and Radicals, there's two words up here that can get kind of tough for kids. The first one is right here. What is it?
Radical.
From now on in this chapter, when you see this word right here, I want you to think the following. You see the word rational, I want you to think what? Fraction. So if I say there's rational exponents, what's that probably mean? The exponent is a fraction, or could be written as a fraction. If an exponent was 2, could I write 2 as a fraction? 2 over what? 1. Okay, rational numbers are simply numbers that can be written as a fraction. Then you see this right here. You see the word radicals? Think this. It's like the nth root of some number. Okay, it's the nth root of some number. So you hear the word radicals, be thinking roots. Radicals simply means find the nth roots pretty much. All right, how about a volunteer to read our essential question? What are we trying to answer here today?
How can you use properties of exponents to simplify products and quotients of radicals?
So we're going to use properties of exponents to simplify products. Products meaning what?
Multiplying.
And quotients meaning?
Division.
Okay, we're going to see what it looks like to take radicals, these things right up here, multiply them and divide them, and use properties of exponents to simplify that stuff. That's what we're trying to answer. So in order to do that, we need to be able to accomplish the following goals. We want to use properties of rational exponents. Rational meaning what again? To simplify expressions with rational exponents. So we're going to look at how we simplify stuff where you have fractional exponents. And then we're also going to use properties of radicals to simplify and write radical expressions in simplest form. Now guys, typically I don't get too worked up about vocabulary. But what I will tell you is, in this particular set of vocabulary, I think that there's one term that's really going to be important. And I think it's this one right here. What does it mean to be simplest form? You okay?
Yeah, I just fell my water.
That's okay. All right.
Hey, the camera caught it.
It did. Oh, that'd be fun. We might be able to turn that into America's Funniest Home Videos and all win $10,000. It'll be a good time. All right, simplest form of a radical. I think if there was one term that's really kind of important to understand, it's this right here. All right. So the first thing I would like is a volunteer to read my definition of simplest form of a radical.
So can you go ahead?
You want it, Grace?
Yeah.
Grace is going to take it.
Okay. An expression involving a radical with an index n is in simplest form when these three conditions are met.
Okay.
Keep going.
Yep. No.
No radicals have perfect nth powers as factors other than 1.
Okay.
No radicans.
Yep. It's pronounced radicans. Yep.
No radicans contain fractions, and no radicals appear in the denominator of a fraction.
Okay, so there's a lot of terms there that we need to satisfy, and we're going to kind of revisit this again. But again, no radicans. What the heck is a radicand? Anybody know that?
Why don't you tell me first?
I'm going to help you. Anybody have an idea? Okay, I'm going to write this down in the box right here. Sometimes we talk about the nth root of some numbers right here. Okay, what we call n, anybody remember what we call n?
Index.
It's the index. Okay, then we have this, we say we find the nth root of some number. Well, that number that's under there, or that term, whatever it might be, that term that's under here, that is your radicand, all right? So the radicand underneath here, just as an example, if I say find the nth root of 8x squared, what's the radicand, kids? 8x squared. It's the part underneath the square root sign, or the nth root sign, or whatever it would be. Okay, so the radicand is just the part that's going to be under that root sign. Okay, so the radicand is simply that number or that expression underneath there. All right? Simplest radical form. I'll talk about meeting those three conditions that we just discussed there in a second, and in terms of what it means to be in simplest form. Kids, I have a typo in this definition for conjugate. Go into this right here. Go to the second line. You see where it says a root c right here in the second line? Change the part, change that radicand of c to a radicand of, that should say b right there. Okay, so it should say a root b minus c root b. Okay, the word is conjugate. Okay, the word is conjugate. And conjugates are going to help us in terms of rationalizing a denominator. And we'll look at what rationalizing a denominator means here, but we just need to understand what a conjugate is. It says the expressions a root b plus c root d and a root b minus c root d are conjugates of each other, where a, b, and c and d are all rational numbers. Guys, this expression right here and this expression right here, what's the difference? Everything looks exactly the same, but between the two terms, one is plus the two terms and one is the difference of two terms. So if I had 3 plus x, what's its conjugate? 3 minus x. If I had cat plus dog, what's its conjugate? So I might say this right here. I might say x minus 4 is a conjugate for what? X minus 4. Don't want to do it that way, Carson. X minus 4 is a, what's the word? Glad I got that one on tape. X minus 4 is a conjugate of what? There you go. It's the same exact terms. You just change the subtraction sign to addition, or addition to what? Okay. Are we okay with that? Yes? All right. Then, the next thing that we have is called, what's it called, kids? Like radicals? Okay, like radicals. That was a saying in the 80s. Everybody was like radical, dude.
Sophie used to be obsessed with the word radical.
Really?
In 3rd grade, I just loved the word radical. And
Sophie, you are so gnarly.
okay. Thanks. Yeah, ask anyone from Dyser.
Really?
Yeah.
Radical.
It was weird addiction.
Radical.
My strange addiction.
Radical.
I dare you to come with floofy hair tomorrow and bandana and really wild curly hair with a ton of hairspray in it.
And her obsession with radical.
Totally rad. They would know about it.
Yeah.
It's cool stuff. Okay, radical expressions. Like radicals are the following. Let me give you an example. 6, 4th root of x, and 9, 4th root of x. Why are these like radicals, kids?
Because they have the index of 4.
Same index for each is what? The index is 4 in each case. All right. How about the radicand in each? Same. It's x down there, right? I'm just simply saying I have 6 4th roots of x and 9 4th roots of x. If I wanted to combine those, how many 4th roots of x are really up there then? 15 4th roots of x. So you have like radicals when you have the same index and same radicand underneath a radical sign. Okay? Sounds pretty cool, doesn't it? Well, better than that, it sounds pretty what?
Rad.
That's rad, dude. So rad. Sophie, I'm so glad that you're in here. You want to know why? Because you make words like that relevant to me when I actually lived through those times.
Yeah. I don't even know how I knew that word.
Aren't you glad that she's so rad?
She's rad. Glad she's rad. I'm so glad Sophie's so rad. She comes in class and she ain't even bad.
Oh,
Oh my
oh,
god.
oh my God.
He jabbed. Oh, I got that wrong too.
Thank God we got this all on film.
We're going to write a mathematical rap about rational exponents and radical expressions.
Ooh.
Oh, wouldn't that be cool?
It's gonna go.
Maybe that should be your assignment.
Oh, that is good. Extra
credit.
credit.
No, I'm just going to say maybe that should be your assignment. You have to film a rap that talks about radicals and rational exponents.
That's our test. Make a rap of our unit. I like that person.
I'm going to write that down. All right, kids, properties of integer exponents. We'll talk about this more, but guys, integer exponents are just like whole numbers. I'm going to just write this. C. I'm just going to write C next page on this because we're going to talk about all of them, all right? I'm going to write C the next page on it because we're going to talk about all of them. Rationalizing the denominator. Rationalizing the denominator simply means no nth roots in the, and I'm going to take the whole thing here. You guys can do the same thing. In mathematics, we say things like this. We say, it's all fun and games until somebody divides by what value? Ah! Dividing by 0 is a bad thing, okay? Math people get kind of upset when they start leaving fractions and they have some kind of a square root symbol or a radical symbol in the denominator, all right? Rationalizing the denominator is going to be a process where we rewrite expressions in an equivalent form so that there is no root in the what? The denominator. So rationalizing the denominator means if you have some kind of a root in the denominator, we're going to do some stuff to it to make sure that that doesn't happen. And I'll show you how to do that, some examples in a little bit. And then lastly, do you guys all remember absolute value? So if I say, what's the absolute value of 6, you would tell me it's what?
6.
And if I said, what's the absolute value of -4, you would tell me it's?
4.
All right. A lot of terms up here, but I got to be honest with you. The term I'm really most concerned about that we understand and what conditions we have to meet is which term? Way up top. Simplest form of a radical. Okay. Anybody need more time with those terms? First question.
We're good.
We're good? Speaking for you or for everybody?
Oh, me. I was still writing that.
All good, kids? Matty J, you good, buddy? Yeah. All right, let's roll to the second page. Let's get all these rules written down. There are so many rules. This core concept is going to be critical to understand. So you might want to highlight this, star this, do what you need to do. I'm going to blow this thing up a bit so I have some room to work. But make sure you know these rules. We're going to provide all the rules. We're going to look at some examples, and then we're going to try and get through example 1 and 2 today. Fair deal? Let's roll, kids. You might want a calculator. I'm not saying you have to have one today, but you might want to have it ready for you. Might make life a little easier for you today. Okay, so core concept says properties of what kind of exponents?
Rational.
Rational meaning what again?
Fraction.
Fraction, or could be expressed as a what?
Fraction.
All right, let's talk. First rule I have up there is product of powers. This is simply saying the following. All right? This is simply saying the following. Product of powers is saying if you have a to the m. Whoops, didn't want to do that. This is simply saying if you have a to the m power times a to the n power, this equals a to the m plus n power. So what's true about my bases there, kids? They're the same. A is the base. So it's like saying, and as an example like this, suppose I have, I don't know, x to the 7th times x to the 4th here, kids. What's this going to equal by rule? Well, your bases are x. How many x's are you multiplying in that first part?
7.
How many x's are you multiplying to it after that? So in reality, how many x's are you really multiplying together? So what's this going to simplify to, kids? Very good. So the rule would be this. When you multiply like bases, simply do what with the exponents? Okay. I don't know how to make that much easier. And we should know that by now. Okay. The next one, what's it say? Power of a power? All right, here's what this is saying. It's like saying, ooh, what if you had like this a to the m, but then you took it to the nth power? So in other words, let's use that example in here. What if you had x to the 7th to start with, and you put that whole thing in parentheses? And I said, take that to the 4th power. That's like saying take x to the 7th times itself how many times? So you'd have an x to the 7th here, x to the 7th here, x to the 7th here, x to the 7th here. I could add those 7 up 4 different times, or I could simply do 7 times what here? Yep. Okay, this simply becomes the following. This rule becomes a to the m times n. So what's this going to be as a simplified solution in our examples? X to the 28th. Very good. That's a bad looking 28, but it is a 28. Okay. All right, power of a product. Next rule. Here's what this rule says. A product. Product meaning what operation? So I might have a times what here, kids? Well, b. And we might take that a times b to the nth power. Okay. This, and you've kind of done this. You guys remember when we were using Pascal's triangle to expand binomials? Okay, you were kind of doing this already anyway. This simply becomes a to the n times, anybody want to guess? Yeah, b to the n. So here was an example. When we used Pascal's triangle, we had to have some expressions like, oh, you might have had 3x right here to the 4th power. Okay, my product inside of parentheses is what times what? We're taking that product to a power of 4. So I have to bring that 4 into the 3, so this becomes really 3 to the 4th. What is 3 to the 4th? Anybody help me out? 3 times 3. Times 3 more. Times another 3. 81. Okay, so 3 to the 4th is 81. And then how about that x to the 4th? What's going to take its position after 81? Okay. So we call this power of a what?
Product.
My product. 3 times x. That's like taking 3x times itself how many times? 4 times. Or 3 times itself 4 times, and x times itself 4 times. Okay? Next one. What's that say? Negative exponent. We've talked about this. If I have a to the negative n, this is equal to 1 over what, kids? I'll try and squeeze this up here, but kids, if I have if I have x to the negative 22 like this, that's a little better for me. If I have x to the negative 22, how would you write that with a positive exponent? 1 over x to the 27. Absolutely, 1 over x to the 22nd. I love it. You guys are good at this. Okay. 0 exponent. Every single value or every single expression to the 0 power except 0 to the 0, which we don't know what that is. They call it indeterminate. But anything to the 0 power, we've always said in here is what? Going to be 1. So if I have a to the 0 power, that's going to equal what value? 1. So if I say, I don't know, 4x squared, all to the 0 power in the end, what's this going to equal? 1, because it's to the 0 power. Right? What's the next one say, kids? Okay, I like this one. This is pretty cool. Guys, this product of powers up here said if you had a to the m times a to the n, same bases right here, what did we do with the exponents in this first example? Add them. So if multiplying like bases meant add your exponents, what do you expect dividing like bases to look like with exponents? Yeah, so as an example, if I have a to the m over a to the n, this is equal to a to the m minus n. Okay? So if I have x to the 26th over x to the 10th, like this, are my bases alike, kids?
Yes.
Those bases are alike. They're both an x. So if I take 26 minus 10, where are you falling at? Down 16. So we'll call this x to the... Okay. And then the last one down here, what's it say? Power of a quotient, okay? Well, like power of a product. We had this product right here. We brought the n into both the a and to the b. Same thing. If I have a over b, like this, and we take this to the nth power, anybody want to guess? So a to the n over b to the n, you bet. So, I don't know. How about 3 over x all to the second power? What's the 3 squared going to get you up top? 9. What's the x squared on the bottom going to get you? So 9 over what? Okay, 9 over x squared. Whew, there's a lot of rules there, kids. A lot of rules.
Calling her a day.
I'm not calling it a day yet, buddy. Whoa, I didn't want to do that, though. But I will do this.
I thought it was 305 now.
Yeah, the 308. We're on the 308, buddy. You know why we're on the 308? Because in this school, student learning is number one. Right?
Hey, we're on recording.
I'm always in trouble anyway, so Hey! Everybody have that down there? Let's put these rules into play. Sound good?
I think we should put this in a frame and hang it in the art.
Beautiful. I would hang it above my fireplace if it was bigger. Okay?
Okay, let's do it, guys.
I think it's beautiful. Okay, example 1 says using those properties of exponents that we just discussed up there. So use the properties of rational. Rational meaning what again? Fractional, or possibly could be written as a fraction. To what?
Radical.
Simplify.
Each expression.
Kids, what are we doing here? 13 to the third times 13 to the 1/6. Give me an idea of what I want to do here. Yes?
Sorry to bother you. The photographer's here for basketball. Where should I send her?
Right down to the main gym and tell her if she wants to tell her, hey, are you still there? Obviously, they didn't want to hear what I had to say.
Is there a button I can push for fun?
Yeah, there's a button back there.
There is a button?
She's probably already gone. Yeah. It's red Peter switched it around.
Okay. Guys, 13 to the third times 13 to the 1/6.
The office?
Yes. We want $1 million.
Okay. I'll get right on that.
Okay, sounds good.
Okay.
Thank you.
You're not even going to tell her? Hello?
That'll be the last time anybody cuts me off mid-sentence. All right. We go 13 to the third times 13 to the 6th here, kids. First of all, what's true of my bases? What are my bases here?
The same.
They're the same. So what should I do with my exponents then? Add them up. So do you guys agree that this is going to be 13? Let me get a bigger pen here. I don't like that. Hang on a second. Where's
What a crazy class, honestly.
This is a 13 to the 1/3 plus 1/6, right? Yeah. All right, now help me out, kids. If I want to add those fractional or those rational exponents up, you help me out. Can I do that?
Change the denominator. Make the denominator.
Yeah. If I'm going to add these exponents up fractionally right here, I've got to have common denominators. So 1/3 in terms of 6 would be what?
13.5.
So 13, 2, 6 plus 1/6, right?
Yeah.
Where's your half coming? You keep speaking of half all the time.
3 divided by 6 is 1.
You're going to reduce to half, right? You bet. 13 to the 1/2 power. Kids, if I had to say we were going to write this as a root, taking something to the 1/2 power is the same thing as doing what, kids? Square root. Absolutely, Grace. Good job. All right, good job. I get concerned about stuff like this second one, okay? Kids make mistakes on this all the time. Maybe put a star by that second one right there, because here's the situation. If you notice right here, there's going to be some things that pop up as we continue to look at these examples. But one of the questions I want you to start asking yourself is this. First of all, how many exponents exist up there everywhere? There's 3 of them. Are any of them the same? Okay, when exponents are not the same, that's bad news. Okay? That's bad news when exponents are not the same. But that doesn't mean that we still can't apply the properties that we want to apply to this. All right? The 2 exponents I'm really focused on about kind of giving us fits are the 1/5 and the 1/4. Okay? When they don't match, that's a problem. Okay? The only thing you can choose to do here is the following. You guys agree that I have an exponent outside of parentheses that I could bring into both? I have a base of 5. I'm going to bring this 5 into this 1/5 exponent. So kids, help me out. That 5 and 1/5, what's the product there?
1.
Okay, so this really becomes 5 to what power first, kids? Okay, times. What's 5 times 1/4? Or how would you express that as an improper fraction?
5.
Now right here, this is why kids get stuck all the time. You know what they want to call that now to the 5/4 power? They want to call it, a lot of people say, you know what, that's 40 to the 5/4 power. Where am I getting 40 from? Okay, but here's the deal. I can't do that because what this is technically saying is this. I agree that 5 to the first is just 5. So I would simplify this as 5 times 8 to the 5/4. But you guys have a dear Aunt somebody that won't allow us to do that. What's her name again?
Sally.
Sally says you better do exponents before you do what? I don't want to multiply this right away because I would have to evaluate 8 to the 5/4 or 8 to that power first. All right? So leave it just like that. Okay? And the reason I'm telling you to leave it just like that is because I really have 5 to the first and 8 to the 5/4. Those exponents don't match, therefore I can't really go much further with it. All right? Now, what I will tell you in this next example is this. Example 2, example 3, and example 1, or this second part and this third part are kind of similar. But if you notice in parentheses right here, I get that like the 5 and 8, we have 12 and 9. But what do you notice about the exponents inside of parentheses with the 12 and 9 this time? There's some things we can do with that. Okay, so what did I say not too long ago? Things to ask yourself each time you start these. Check to see if some of the exponents are the same. If they're different, is that a good thing or bad thing? That's bad. But if the things are the same, that can be what? We're going to apply the same thing that we just did here. Let's bring that negative 1/3 into both exponents. So you guys help me. What's negative 1/3 of this exponent 3? You guys all buy that I can call this 12 to the negative 1 right now, first. Times what?
9 to the negative 1.
Okay, 9 to the negative 1. Now at this point right here, kids, what ends up happening is it says, well, you've got the same exponent. Okay? So a couple things I could do, a couple different directions I could go. And I think the easier direction to go is to ask you what you think you might do next. How could I express this, or each term in this expression? How could I write those maybe? 1 over 12. Okay, I agree. All agree that this is the same as 1 over 12? And so could I take 1/12 times 1/9 to get 1 over? Woo, that'll work, right? Let me show you another way about this. This is going to work. But another way about this could have also been the following. Kids, isn't it like they brought negative 1 into both of these right here? Couldn't I have written this as 12 times 9 to the negative 1 power? Like that. What is 12 times 9, kids?
108.
This is like 108 to the negative 1 power, which would still be the same as what? 1 over 108. So if you make the connection, it says, ooh, this exponent and this exponent are the same, we could really call this 12 times 9 all to what power? Okay, that would work as well. Okay, that would work as well. Okay, let's finish these last two and we'll call it good for today, all right? Next one, pretty simple. This is really 8 divided by 8 to the 1/9. So I have like bases there. And since we have a quotient of like bases, what are you going to do with the exponents? This is really up top, 8 to how much? So you're really going to say this is 8 to the first minus what?
8 minus 8 to the 1/9.
Okay, so 1 minus 1/9 as my exponent would make 8 to the 8 to the 8/9 power. Okay, I know I'm going quickly here. Are you following so far? Take a look at the next mess we have up there. Let me ask you this question. Are some of the exponents the same or are they all different? Some are the same. So is that a good situation or a bad situation? This could be good for us, right? Here's how we're going to simplify this. First of all, my suggestion, kids, bring the 3 into what first? Okay, I'm going to bring the 3 into the 1/4 each one in the numerator and denominator. So this becomes 56 to the 3/4 over. Okay, now let me show you what's going on here. Guys, we taught these rules all the time. They work the same forward as they do backward. If the left side is equal to the right side, then that means the right side is equal to what? Left side. If I say this, 2 plus 2 is equal to 4, I can say, well, 4 is also equal to what? 2 plus 2 working backwards. Well, kids, it's almost like somebody had 56 over 8 right here, and they brought in what exponent each time? So do you guys agree I can work backwards and say, you know what, this is really the quotient 56 over 8. Since these powers are the same, I can say it's this all to the what, kids? You guys see what I'm doing there? Because if there's parentheses like this, I could bring this power in to both the numerator and the denominator.
Office before leaving today. Lucy Bork, Silver Schmidt, Seth Peterson, Bryce
7 to the what?
Brock Meyer, Mark Mahood, Max Eikamp, River Grove, Trevor